In this video, so first we'll talk about what it means to be even and odd. Graphically, an even function is symmetric about the y-axis. An odd function has symmetry about the origin. Analytically, an even function means that f of negative x is the same as f of x. An odd function is f of negative x is equal to negative f of x. So some examples of even functions include 1, x squared, absolute value of x, and cosine of nx, and cosh of nx. So for example, x squared, if I plug in 2, x squared would give me 4. If I plug in negative 2, I still get the same number, 4. Examples of odd function include x to the third, sine of nx, and sinh of nx, and x to the 2n plus 1. So for example, if we look at x to the third, using our 2 and negative 2 example, when I plug in 2 here, I will get 8. When I plug in negative 2, I get negative 8. Some properties of even and odd functions. The sum or difference of two even functions is even, and the product and quotient of two even functions is also even. The sum or difference of two odd functions is odd, and the product quotient of two odd functions is even. The sum or difference of an odd and even function is neither even nor odd, and the product or quotient of an odd and even function is odd. And last, the integral properties. If f is even, then you can see what would happen if you integrate from negative L to L. This is symmetric so you can break this up into negative L to 0 and 0 to L, and the f of x for the negative L to 0 is going to have identical values from 0 to L, and therefore you're going to get twice 0 to L f of x dx. If f is odd, however, from negative L to 0, you'll get negative the values you get from 0 to L, so they will cancel out and you'll be left with 0. Next, we'll look at cosine and sine series. So if f is even, then when you go to do your Fourier series, you'll see you have your a sub n, which multiplies f times cosine. So this will be an even function, so you can use this property of integrals here. So it'll be 2 over L, 0 to L, f of x cosine of n of your normal cosine. And then what you'll see for your odd, your b of n, when you multiply your f of x times an odd function, it'll be odd. So when you integrate from negative L to L, you'll get 0. Similarly, when f of x is odd, when you multiply an odd times an odd, so where do we have the product of two odd functions? That's over here. The product of two odd functions is even. So that means your b sub n's will then add together, and your a sub n's, now your a sub n's will be an odd function because you'll have an odd function times cosines, which would be even. So an odd and an even here, an odd and an even function is odd, so integrating over negative L to L will give you 0. Last, we'll expand a Fourier series. So if we're interested in integrating or representing a function between 0 and L, we can expand our definition of the function to go from negative L to L in such a way that we have an even function, in which case we can get a cosine series, a Fourier series with just cosines where the b sub n equals 0. Or we can expand in a way to get an odd function, and therefore we only will have a sine series. And there are many reasons to do this. One may be dictated by your problem, or another may be because one of the series, the cosine series, may converge faster than the sine series, or the Fourier series with both sines and cosines. So that's kind of an overview, and we're ready to start looking at our material. So first we'll look at even and odd functions. For even functions, f of negative x is equal to f of x. So an example would be x squared, because if I had f of x, let's say x equals 2, that will be equal to 4, and that's the same as f of negative x. And if we plot an even function, you'll see this symmetry about the y-axis. In other words, this side of the axis looks like this side of the axis. If you fold your piece of paper over, it would match up. Here we have odd functions where f of negative x is equal to negative f of x. So for example, x to the third, again using our 2 and minus 2 example, f of 2 is equal to 8, whereas f of minus 2 is equal to minus 8, which is negative f of 2, which is exactly the form for an odd function. And odd functions have this symmetry about the origin. To see this symmetry, I have outlined my graph for the positive x-axis, and I've outlined this in blue. And what I'm going to do with this is I'm going to flip it so that it's a mirror image of itself. Now I've outlined this in green, and what I want to do next is I'm going to flip it up down. The idea then is I brought the bottom part here to the top and the top to the bottom, almost as if I flipped the piece of paper. I'm going to try to rotate this so you can see. Okay, so now I'm going to try to rotate this so you can see. Just flip back to here. And now this is exactly the shape that comes down to the negative axis. That was actually a lot of work to demonstrate that symmetry about the origin, but it's kind of two types of flips. One, so that it's symmetric or a reflection of each other, and then top to bottom. And then you move it over to the negative axis. And for odd functions, f of 0 is always 0. Then next we have these properties that the sum or difference of two even functions is even, and the product and quotient of two even functions are also even. The sum or difference of two odd functions is odd, and the product quotient of two odd functions is even. And then the sum or difference of an odd and even function is neither even nor odd, and the product quotient of an odd and even function is odd. And we're going to prove one of these before we look at the last property. I am going to do proofs for two odd functions. The two even and odd follow similar patterns. So I'm going to assume f1 and f2 are odd. So in other words, f1 of negative x is equal to negative f1 of x, and f2 of negative x is equal to negative f2 of x. And then I want to see what happens when I take the sum of these two odd functions. So I'm going to let g of x equal to the sum of f1 and f2. So now what I need to do is look at g of negative x, but that's going to be equal to f1 of negative x plus f2 of negative x. But since f1 is odd and f2 is odd, what I get is that's equal to negative f1 of x plus negative f2 of x, which is equal to negative g of x. If I plugged in x into here and then put a negative in front at the very end. So I've shown that the sum of two odd functions is odd. You know what? For the product, instead of doing odd, let's assume f1 and f2 are even and look at their product. So f1 of negative x is equal to f1 of x, and f2 of negative x is equal to f2 of x because they're both even. I use this e for the last of the r and the beginning of even. Anyway, so our product g of x, if I multiply f1 of x times f2 of x, and then I plug in negative x, I get f1 of negative x times f2 of negative x. Because these are both even functions, this will equal to f1 of x, f2 of x, which is just equal to g of x. So now I've shown that g of negative x is equal to g of x, meaning the product is also even. The other properties for 1, 2, and 3, the other different combinations, I'll let you try on your own. What I will do next is proof of these integral properties. We will start assuming that f is even. So we want to prove that the integral from negative L to L. So remember, the key here is that it's symmetric about the origin. So negative L to L of f of x for f being even is equal to 2, 0 to L, f of x. So I start by rewriting my integral from negative L to L. I break it up into two integrals, negative L to 0 and 0 to L. And what I want to note is this negative L to 0 f of x is equal to negative L to 0 f of s. So here my limit of integration instead of negative L is now L, but I have a negative sign out here. And to see this, what we're going to do is this substitution. As you see, we went from x to s. Even though it's just a variable of integration, we did this by substituting s is equal to negative x. Then ds is equal to negative 1. And then if x goes from negative L, that means S must go from positive L, and then they both go to 0. Making this substitution now, I have my integral. Instead of going from negative L to 0, I'm going to go from, S is going to go from L to 0. And then my f of s, because I'm substituting s for x, but now instead of dx, I need to have a negative 1 ds. So this is how I get this formula here. So plugging that in now, our integral from negative L to L, f of x dx, is equal to, now we said that was negative L to 0, f of negative s ds, plus our 0 to L, f of x dx. And now further, because f is even, this f of negative s simply becomes f of s. So now what you can see is these integrals are identical except for a different variable, but that doesn't matter, it's just the name of the variable, and the order that the integration limits are. So instead of going from L to 0, this one goes from 0 to L. So to remind you what happens if instead of going from a to b, well, let's look at the integral, a to b f of s ds. Well, that's f, capital F, that's the antiderivative of lowercase f of b minus f of a. And that's minus f of a minus f of b, which is equal to minus b to a f of s ds. So when we swap the b, a, and b, what we do is we get a negative for our integral. It's the same answer, just with the negative sign. And so here we can swap the order of these limits, so we can go from 0 to L, but this negative becomes a positive. And what you see is we have the same integral twice, so that's 2 times 0 to L f of x dx. You can do something similar when f is odd, and you will see when you go from negative L to L, f of x dx is equal to 0, essentially because you won't be able to switch this from negative s to positive s. So at the end, you'll have this extra negative sign here, so these two will cancel out and you'll get 0 at the end. Now, if I combine the integral properties here, along with the product of even and odd, and then I go back and I look at my Fourier coefficients, if f of x is even, that is if f of negative x is equal to f of x, when I calculate my Fourier coefficients a sub n and b sub n, when I look at my cosine coefficients, because f of x is even and cosine is even, so I have an even function because the product of two even functions is still even, I'm going to get 2 times L over integrate only from 0 to L, f of x cosine of n pi x over L dx. And remember, this is the form of our Fourier coefficient. Now when we look at b of n, we're going to have f of x, again, f of x is even, sine of x is an odd function. So when we go from negative L to L, when we integrate from negative L to L, the product of an even and an odd function, where do we have that? The product of an odd and even function is odd. So when we go from negative L to L, we're going to get 0. Similarly, when f of x is odd, in other words, f of negative x is equal to negative f of x, now when we look at in our Fourier series, our sine coefficients, we're going to have an odd function times the odd sine. So an odd function times an odd function. So the product of two odd functions is even. So now we're going to have to multiply our integral by 2, and we can just go from 0 to L of our function times our sine. An, on the other hand, f of x is again odd, and cosine is even, and a product of an odd and even function is odd. So now when we integrate from negative L to L, we're going to get 0. So this is kind of what we were after. So if f of x is even, it's possible to write a Fourier series with only cosine terms, and that would be called a cosine series. If f is odd, it's possible to write a Fourier series with only sine terms, and that would be called a sine series. So I have this here kind of summarized. So when f of x is even, then we can write our cosine terms. We have this formula for cosine terms. This is the simplified form here. and all of our sine terms will go away. Our b sub n is equal to 0. When f of x is odd, we can write this as a Fourier series of only sine, a sine series here, and then our a sub n can go away. And the example we will look at is f of x is equal to x. We're going to integrate from negative L to L. We're going to let f of negative L and f of L equal 0. Let f be defined elsewhere so that it's periodic with period 2L. The function defined in this manner is known as a sawtooth wave, and we'll see that. Graph 3 periods of y of f of x, y equals f of x, and find the Fourier series for this function. And here I have my graph. So f of x is equal to x for x between negative L and L, not including L. And so that's just this portion of the graph. And then I made it periodic. Also, I have f of negative L is equal to 0, so that's dotted in here, and f of L is equal to 0. So there are discontinuities here. So this is the main portion of my graph, but then I just repeated it so that it would be periodic. If I wanted to kind of connect these a little bit, this is why it would be called a sawtooth, because it has sort of that shape of the saw, right? The sawtooth, the pointy edges here. As far as the Fourier series goes, f of x equals x is an odd function, so we can write it as a sine series here, where our a sub n's are equal to 0. Our coefficients for cosines are all 0. Our b sub n is given by this formula here. So now we no longer need to integrate from negative L to L, but we need to double our integral, so that's the 2 over L, and now we can integrate from 0 to L, f of x, which is equal to x, sine of n pi x over L dx. And I have the integral here. I did have to use integration by parts, but we've done a lot of these integrals in previous videos, so I'll just say at the end, we come up with minus 2 over n pi, L cosine of n pi minus 0, plus L over n pi squared sine of n pi minus 0. A couple of things cancel out. Of course, the zeros go away. Also, sine, since n is an integer, because n is, where does n comes from? It comes from the summation, the a sub n, like we have discrete values of n. So this here will also go to 0. So what we're left with, and cosine of n pi is equal to negative 1 to the n. So what we're left with is minus 2L over n pi, and then our cosine n pi is negative 1 to the n. Everything else went away. So we can rewrite that as 2L over n pi minus 1 to the n plus 1. So I have my a sub n equals 0, and then I just moved my coefficients. B sub n is equal to 2L over n pi minus 1 n plus 1. I moved it up here so that I have space to write my Fourier series, which only has terms of sine, so it's a sine series. So I have my 2L pi here. My n is going to be part of my summation, n going from 1 to infinity. My negative 1, n plus 1 over n, that over n comes from here, and then sine of n pi x over L. And then I wrote out the first few terms over here by plugging in n equals 1, 2, and 3, etc. into my series. If I look at my graph that I have in blue, that's my graph of my function that was given to me, versus this sine series, which I have in green, and this is a partial sum because I can't really compute it all the way out, but I get I can see the Gibbs phenomena. Every time there's a discontinuity, I kind of overshoot a little bit before I settle back into something that approximates my real f of x. So the first note, in this example, f of negative L and f of L is equal to 0, as well as f of 0 equals 0. Remember, f of 0 equals 0, that's a requirement for an odd function. And then here, because we wanted to write a sine function, this is also a requirement that the function must be 0 at x equals 0 and x equals L to be, basically to be both odd and periodic. Another thing to note, I moved my sawtooth wave graph and my sawtooth wave function sine series. So in our first video about Fourier series, we represented a triangle wave with a cosine series. which involved representing f of x equals x as a cosine series on the interval 0 to 2. And this is what it looked like. This was the problem we did a couple of videos ago. We had a triangle wave. We did the Fourier series, and it turned out that our sine coefficients were all 0. And we didn't do anything to make it that way. It just happened that way. And then we saw that f of x was equal to a cosine series. So looking at this, if L is equal to 2, if we wanted to approximate f of x equals x, just say, let's say from 0 to L, or 0 to 2. Let's say L is equal to 2. We can either use this sine series here, or we could come over here and just to approximate 0 to 2, we could have used this cosine function, this cosine series. Either one would have worked. So again, looking at this, to represent f of x on x between 0 and 2 by a Fourier series, we can do this with either a sine, the way we have over here, this sine series, or with a cosine series, which we have done here. Thus, to represent f of x equals x on 0 to 2 by a Fourier series, I just said this, right? We can do this either with a sine or cosine, and for a cosine series, f is extended to an even function. Remember here we had an even function. And for a sine series, we have an odd function. If f is extended any other way, the resulting Fourier series will still converge, but will involve both sines and cosine terms. Then the question is, how should we represent this? Should we represent with a sine series or a cosine series? And often the form is dictated by the purpose for which it is needed. If, however, there's a choice to be made, often the one that converges the fastest. Note in our example for f of x equals x, the triangle wave converges faster, right? Because the terms here are decreasing, our coefficients are decreasing at a rate inversely proportional to the square, where here the terms are decreasing linearly. So this is converging faster. And basically because it's a smoother function, it doesn't have these big discontinuities, and therefore it's easier to approximate. Okay, so the rest of our video is going to be talking about expanding a Fourier series so that we can have an even periodic expansion or odd periodic expansion, sort of like what we were talking about before when we wanted f of x either as a sine series or a cosine series. So here we can choose. And the first one is, if it's an even periodic expansion, in other words, we want a cosine series, we're going to expand our function. So if we're interested of f of x on the interval 0 to L, we're going to expand the function so that it is an even function. So from negative L to 0, we're going to have g of x is equal to f of negative x. And then for an odd periodic expansion, or a sine series, our h of x. So we know that f of x goes, what f of x is between 0 and L. To make it an odd expansion, we're going to have 0 at the origin and at L. That's a requirement. And then for negative L to 0, we're going to expand our function to go from, so that h of x is equal to negative f of negative x. So we'll do some examples. Oh, and there was one other thing. Sometimes it's convenient to define a function k of period 2L such that k of x is equal to f of x from 0 to L, and it's equal to, could be anything that's convenient between negative L and 0. So let's do some examples. Oh, and I should also mention, so maybe it goes without saying, but there are infinitely many series which converge to f of x in the original interval. So the matter is choosing which one you want to do. In general, on homework, you'll be told which one you want. So let's look at expanding a Fourier series of period 2L when our series is defined on 0 to L. Here is sketch the graph of 3 periods of the sum of each of the sine and cosine series for x goes from negative 6 to 6. So here's our original f of x, and it's defined between 0 and 1, and it's defined as 1 minus x. It's defined as 0 between 1 and 2. Just to get a feel of what's going on, I'm going to sketch the original function. So we have this from 0 to 1. We have our line that goes from 1 to 0. And then from 1 to 2, we're at 0. So that's kind of this is our original function f of x. And then we're going to go ahead and say, well, it's periodic, L is equal to 2, so it looks like this here. I'm going to move our graph up here for our reference, and now I want to look at the sum of the cosine series. I'm going to do the cosine series first. So I need to expand my definition. Right now, what I have is f of x defined between 0 and 2, so L is equal to 2. But I want to expand this, so I go from 0 to 2, so that I have an even function. So when I do my Fourier series on my function, I'll get a cosine series. So g of x is going to equal to f of x between 0 and 2, and f of negative x between negative 2 and 0. And I'm getting that just straight from this definition. So g of x is equal to f of x for the positive portion, and f of negative x for the negative portion of my period. So here, f of x, I can just write this here. I have two subintervals. I have the interval 0 to 1, which is 1 minus x for my definition. And for the interval 1 to 2, I have 0. So this part is easy. The x going from negative 2 to negative 1, it's just 0. Whenever it's 0, that's easy. From negative 1 from negative 1 to 0 now, what I need is f of negative x, which I've written here, f of negative x. So if I plug in negative x into f of x, I'm going to get x plus 1. So that is exactly what I have here. And if you think about it, if here I have 1/2, I'll get 1 minus 1/2 is just 1/2. And over here, I wouldn't have 1/2, but I'd have negative 1/2. And when I plug that in, I'll also get 1/2. So I have sort of this even expansion now. And specifically what I have is I have this graph now. I have this positive half, which looks just like f of x. But now I've expanded it, so I also have the negative half of my graph from negative 2 to 1, but I expanded it to be an even function. So you can see the symmetry about the y-axis. And you can see that now I have 1 plus x when x goes from negative 1 to 0, and then 0 between negative 2 and negative 1. And then once I have this part of my graph, I can make it periodic. So the reason why we are doing this, and we're going to do some examples in a minute, but first we also have to compare this to a sine series, is we've had this function here, and if we want to get an estimate of its value somewhere between 0 and 2, where it's defined, right, between 0 and 2. Of course, this is such an easy function, you wouldn't actually, well, anyway, let's not get to that. But let's say you wanted to estimate this function between 0 and 2. What you can do then is expand this function to an even function, g of x. And then this even function, then we can use to get a cosine series using this formula here, which we had mentioned earlier. And you'll see examples of this. So I'm just going to tell you, hang on a little bit longer, and you'll see this whole process all the way down to our cosine series. But first, we want to look at an odd expansion for a sine series. And here is our formula. H of x is equal to f of x between 0 and L. In this case, L is equal to 2. It's equal to 0 when x is equal to 0 or L. And it's negative f of negative x between negative L and 0. So I've written this formula here, just plugging in 2 for L. And then, of course, because between 0 and 2, we've broken this up into two subintervals, I need to reflect that. So between 0 and 1, we're at 1 minus x. Between 1 and 2, we're at 0. X equals 0 or 2, we're at 0. And now the reverse here, we'll do this part first because it's easier. When we go from negative 1 to negative 2, that's 0. And then to go from negative 1 to 0, well, that's going to be equal to negative 1 to 0 minus f of negative x, which I've written here, minus f of negative x. So when we plug in negative x into f of x, we get 1 plus x. And then the minus in front of it gives us minus 1 plus x. So that's exactly what I've written here. And you can see what that gives us is we have for our positive, it's exactly the same as our original graph. And then for our negative, we're going to When we go from 2 to negative 1, we're at 0. From negative 1 to 0, now we have this line here. And this, you can see, this graph is an odd graph from here to here. And then we can continue it to make it periodic. And just to compare, for our sawtooth wave here, this was our original function, we can expand this, just take this little piece here and expand it so it's an even function, or we can expand it so it becomes this odd function. And both of these are valid when we do a cosine series, especially because we're only interested in estimating from 0 to 2, which both of these functions match our original function. But the expansion to an even or an odd function gives us the ability to represent a cosine series or just a sine series. And now is a good time to do an example where we go all the way through. We want to find a cosine series, period 4, for this given function here. Sketch the graph to which the series converges over 3 periods. So f of x is equal to 1 when x is between 0 and 1, and it's 0 when x is between 1 and 2. I have our relevant formulas here for the cosine series. It's an even periodic expansion, so I have g of x for an even expansion, and then I have my formula for a sub n for my cosine coefficients, again for an even expansion. For whatever reason, I always like to graph my original graph. So I go from 0 to 1 and I'm at 1, from 1 to 2 I'm at 0. And I expand it out so that I have my periodic function. And just to note, this function clearly is not even, right? 1, I guess you could make it periodic, but when you come over here, right, f of negative 1/2 is 0, whereas over here f of 1/2 is equal to 1. So it's clearly not an even function, which is why we're going to expand this definition in a way that it is even. And once we have an even expansion of the function, we can make a cosine series. So I move my graph of my original function here, and I will start looking at g of x for an even expansion. So I have my f of x for x between 0 and L. So between 0 and 1, we're at 1, and between 1 and 2, we're at 0. Now we need to look, well, this one's going to be easy. Between negative 1 and negative 2, we're going to be at 0. Now between negative 1 and 0, I want this to be equal to f of negative x. So when I plug in negative x into my f of x, I just get 1. So that's my new equation. So I'm going to have my same original function on the positive side. On the negative side, between 0 and negative 1, I'm going to have 1. And then between negative 2 and negative 1, I'm going to have 0. So you can see that this is an even function with symmetry over the y-axis. So I put my graph of my expansion here, and I'm going to start calculating my coefficients, just like I used to do a couple of videos ago for Fourier series. So A naught we often do separate because your cosine of zeros and your sine of zeros simplify pretty quickly. So using this formula here, right, this is the original Fourier formula, but because it's even, we can use the simplified formula. So we have 2 over L, so that's 2 over 2 in this case. We're going to integrate from 0 to L, so 0 to 2, f of x, cosine of n pi x over 2. Again, we have to break this down into two separate integrals. From 0 to 1, we get cosine, 0 to 1, we have f of x is equal to 1, and then cosine of, and now we're plugging in 0 for x, so we get cosine of 0 dx. Then from 1 to 2, our function is 0, so we have 0 dx. So what we're integrating is from 0 to 1, cosine of 0 is 1 dx, which is simply equal to 1. For a sub n greater than 0, we have 2 over L, which again, L is 2, so that's 2 over 2, 0 to 2, f of x cosine n pi x over 2 dx. Separating to the two integrals, I have 0 to 1, my f of x is equal to 1, so I have cosine of n pi x over 2 dx. And then 1 to 2, our f of x is equal to 0, so that's just 0 dx. You can see my integrating skills over here. So my final answer for a sub n is equal to 2 over n pi sine of n pi over 2. When n is even, this will cancel out and this sign will go to 0. When n is odd, so in other words, n is equal to 2k minus 1, our answer is going to be 2 over n pi times negative 1 to the k minus 1. So now I can plug in my coefficients into my formula for Fourier. That is our a naught over 2, which is 1/2, plus over here I'm going to first use this form. So I'm going to use my summation m is equal to 1 to infinity. So I'm going to pull out my 2 pi, and then I'm going to have my 1 over m, and then sine of m pi over 2. This is my coefficient. This sine term is my coefficient, because once I run my sum from m equals 1 to infinity, I can evaluate my sine of m pi over 2, and this is just a number. And this is going to be my coefficient for cosine m pi x over 2. Remember, this is a function of x. So this is a cosine series. Even though the sine appears here, don't be fooled. The sine, once you plug in your m's, this becomes a number, and this is your cosine function because of the x here. And then, as I said, you can convert it to this form here if you'd like. So I have one more example, and this one is going to be a sine series. So I have my odd periodic expansion formula here, as well as my Fourier coefficient formula over here. So find the sine series period 6 pi for the given function. Sketch the graph to which the series converges over 3 periods. So f of x is equal to 0 when x is between 0 and pi. It's 1 when x is between pi and 2 pi, and it's 2 when x is between 2 pi and 3 pi. As I had mentioned, even though they don't ask for it, I like to sketch the graph of the original f of x. So it's 0 between 0 and pi, and it's 1 between pi and pi over 2, and it's 2 between 2 pi and 3 pi. So this is my original series here, and I went ahead and made it periodic. Now we need to determine our h of x, which we have the formula, or the form is over here. But of course we have to bring in all the sub-intervals. So to go between 0 and L, our original range here, it's just equal to f of x. So I've recopied this f of x into here, except I reversed the order because I feel like we should go from smallest values of x to largest. So I have x between 2 pi and 3 pi is equal to 2, x between pi and 2 pi is equal to 1, x between 0 and pi is equal to 0. So this is just the same as our f of x. And then next, on our formula for h of x, we need x equal to 0 and L is equal to 3 pi, equal to 0. So I have x equal to 0 and 3 pi is 0. And then last, we need to start looking at the negative of these intervals. So I listed them as negative 3 pi to negative 2 pi, my negative 2 pi to negative pi, and my negative pi to 0. This one's easy because it's just 0. When I look at this interval from negative pi over 2x to negative pi, I often forget my x is now negative here. So I picked an x in this interval, negative 3 pi over 2. So by this, my h of x should be equal to negative f of negative x, which will give me my positive 3 pi over 2. So I look up 3 pi over 2, and that would give me 1, but I need a negative for my h of x, so that's negative 1. And you can also, you could probably do this just as quickly without all this extra stuff, but as I said, I often forget that I have this, that x is negative. But anyway, so similarly, I can then look at h of x is equal to negative f of negative x. I can remember that my x is negative, so I can look up the positive value of x between 2 pi and 3, and I get 2, but then I need to put the negative in front. And you know what? Rather than write 6 lines of h of x, I'm just going to say it looks like f of x for the positive values of x, and then for the negative values of x, I wrote down my values of h of x. So now I can look for, I could have pasted that whole chart of h of x here. That would have been fine too. So now I'm ready to find my coefficients b of n. It's equal to 2 over L. L in this case is equal to 3 pi. So 2 over 3 pi. the integral from 0 to L. And that's, in this case, 0 to 3 pi, except we're going to break it up into 3 intervals. And so the nice thing is, this is another reason not to paste all of h, is now, because it's an odd function, we only have to deal with the positive portion. I feel like I did a lot of work on that h of x, but anyway, in case someone asks you. So I can go from 0 to pi, pi to 2 pi, and then 2 pi to 3 pi. And I have my f of x, which is 0, f of x is 1, f of x is equal to 2, and then I have my sine n pi of x over L, which is 3 pi. The rest is integration and evaluating. I did combine two terms here. So you can look that over, but this is my answer for my coefficients, my sine coefficients b sub n. And then I plug that into my formula, my huge long coefficient here. And remember, this coefficient becomes a number once you run your summation 1 to m, right? You just plug this in, and these cosines become numbers, whereas this sine here, because these are coefficients in front of your sine terms, your sine will stay, well, your m will still be here, but your x, that's your variable x. You'll have your sine mx over 3. So this is my Fourier series, which is in particular a sine series because it only has sines. Remember, these cosines are just coefficients, they become numbers. To review what we looked at even and odd functions. We said graphically, an even function is symmetric about the y-axis, and an odd function is symmetric about the origin. Analytically, an even function means that f of negative x is equal to f of x, and an odd function, f of negative x, is equal to negative f of x. And we had some examples of even function, in particular cosine is an even function, and sine is an odd function. We looked at these properties of even and odd functions. So the sum or difference of two even functions is an even function. The product or quotient of two even functions is also an even function. Similarly, the sum or difference of two odd functions is odd, and the product or quotient of two odd functions is even. So this is kind of different. Then the sum or difference of an even and odd function is neither even nor odd, but the product or quotient of an odd and even function is odd. And then we found this other integral property. So if we have an even function and we integrate symmetrically from negative L to L, then our integral is equal to 2 times the integral integrated from, or with the limits of integration 0 to L. So we double the integral and half our limits of integration. Whereas if it's odd, we see that our symmetric integral from negative L to L will give us 0. And you can kind of see the reason for this, because when you plug in these negative values in for f of x, they just become equal to f of x. So in effect, you're going to double your integral from 0 to L. Whereas here, when you plug in your negative limits of integration, your negative L's here, those are going to become, because it's an odd function, negative f of x. And so those will exactly cancel out when you plug in your positive values of your limits of integration. And so you'll get 0. Next, we sort of combine these ideas that cosines even, sines odd, these products of two even is even, the product of two odds is even, and the product of an odd and even is odd. And we looked at what that means for Fourier series. So if f of x is even, in our Fourier series, we're multiplying an even function times another even function cosine. So what that means is our formula for our cosine coefficients, if f is even, can be converted to this formula here, where we have twice the integral, but now we integrate from 0 to L. And then because f is even, when we multiply by our sines to find our sine coefficients, that means we'll have an odd function, meaning our b of n will go to 0. If f of x is odd, then when we multiply by our sine, we're going to get, well, what is it? The product of two odd functions is even. So we can take our formula for our coefficients and we can use this other formula here. because now we have an odd function, f of x times sine, which is also odd. So we have an even function. So we have twice the integral, but we're integrating from 0 to L. Whereas our cosine coefficients are a sub n, since cosine is an even function times an odd function will give us an odd function. So when we integrate from negative L to L, we're going to get 0. So our a sub n is 0. So what we get is a pure, in this example, if f of x is even, a pure cosine series. Or if f of x is odd, we can get a pure sine series. And last, we talked about if we have a function defined between 0 L that may not be, it's not even or odd, we can expand the function to make it even using this formula here, or we can expand the function to make it odd using this formula here. And by doing so, once we expand the function, we're really interested in the function between 0 and L, but we can expand the function and then make a pure cosine or a pure sine series. And then that will be valid on the interval 0 to L for our original function. So that's it for this video. Thank you for watching.